Welcome, everyone. I'm Neal Mangaokar, and today I'm going to be talking about some work we conducted at Virginia Tech, where I just completed my undergraduate degree. Specifically, we're going to be talking about the new threat of deepfakes, but in the medical domain. Now, in case you're not familiar with deepfakes, I'll go ahead and give you a brief background. Take a look at these images of people. None of these people actually exist. They're deepfake images. And a deepfake image is one that's been generated or manipulated using artificial intelligence, specifically deep neural networks. In fact, deepfake images are generated using a very specific one, the Generative Adversarial Network, or GAN. A GAN, in short, is a pair of deep neural networks that learn in tandem with one another to synthesize high-quality deepfake images. And as you can see, these deepfakes can be very believable. And people have started discussing the serious threat posed by deepfakes on the web. A bad actor can use them to create fake social media profiles, fake pornography, and so much more. An example is Facebook, right? They recently announced that they've been forced to remove accounts that used AI to create fake profile pictures. Today, however, we want to look at deepfakes from another security angle. We want to ask, are deepfakes a threat in the medical domain? So let me walk you through an example in which medical deepfakes can be used to mislead medical diagnostics. Say a healthy person walks into a medical institution and gets their x-ray taken. This healthy x-ray falls into the hands of a bad actor who's compromised the medical imaging pipeline. This bad actor can use an algorithm to change the healthy x-ray into a medical deepfake with signs of a specific disease. Here, it's an enlarged heart or cardiomegaly. The x-ray is then diagnosed by a doctor or a machine learning tool, and you're now believed to have the disease. So let's talk about why an attacker might be motivated to create such a medical deepfake and what the fallout might be. The biggest motivation here is financial. Take, for example, a malicious clinic triggering misdiagnosis to collect insurance payouts for unnecessary treatment. And of course, such an attack would also have devastating consequences for the patient. They would undergo mistreatment and forego unnecessary medical expenditure. And it's also important to note that the attack scenario we're talking about is very plausible, and this is due to vulnerabilities exposed by medical infrastructures. Medical images are usually stored in a PACS, or a picture archiving and communication system. And recent work at USNICS 2019 demonstrated that a medical PACS in a hospital can be compromised. An attacker can access the medical data, either at rest, on the server, or in motion. And this is possible because these real-world systems follow poor security practices, misconfigurations, use of default credentials, and so on. And these poor practices, they leave them exposed to attacks, including man-in-the-middle interceptions, unauthorized HTTP access, and even social engineering attacks. So hopefully by now it is clear that a medical deepfake attack is both motivated and realistic. So let's talk about the criteria the attacker needs to meet in order for this medical deepfake to be successful. Well, the attacker needs to convert a medical image for a healthy patient into a deepfake that, 1, indicates an attacker-chosen disease condition, and 2, manages to do so while preserving the patient's identity, that is, anatomical characteristics. And this second goal is important because a deepfake will not be successful if the doctor or machine learning tool easily notices that the patient is anatomically different. Now that the attacker has his goals in mind, he can identify the targets of his deepfake creation as medical professionals and diagnostic machine learning tools. Both medical professionals and these tools must believe that the image shows signs of the disease and that the image is real and belongs to the same person. In keeping these goals in mind, we discovered that one can generate medical deepfakes using neural image style transfer techniques from computer vision. How? Because generating a medical deepfake at a very high level asks that we take as input a non-disease image and convert it to one that has a disease, all while preserving content or patient identity. And if we view the non-disease state as the original style and the disease state as the target style, then an image style transfer strategy makes a lot of sense. Now, state-of-the-art approaches for image style transfer employ GANs. And in fact, we chose a very specific style transfer GAN called CycleGAN. CycleGAN works really well in this scenario because all it requires are several images from the non-disease category and several images from the diseased category. Using these images, it learns to translate a previously unseen image from the non-disease to the disease category. Recall, however, that we do need to meet explicit attacker goals. And so we need to add additional training objectives to CycleGAN in order to meet them. The first is the disease objective, which enforces that the disease is explicitly injected. And to this end, we use an externally trained disease classifier that provides optimizable feedback about whether the output deepfake image has the disease or not. The second is the identity objective, which enforces that patient identity is explicitly retained. And to this end, we use an externally trained identity classifier, which gives us similarly optimizable feedback, but regarding identity retention in the deepfake image. The CycleGAN style transfer framework with these two added objectives comprises Jekyll, a GAN-based medical deepfake generator. So we went ahead and evaluated Jekyll. An evaluation, of course, checks whether we satisfy the attacker's goals. So we began by recruiting 3 trained doctors who have extensive experience dealing with x-rays. We gave these doctors deepfake x-rays and asked them if they showed signs of the disease cardiomegaly injected by the attacker. And in 80% of cases, a majority of doctors said yes, which told us that Jekyll can convincingly inject disease. We then gave them multiple images, some deepfake, some real, and told them that some of these images were fake, created by an AI. And we then tasked the doctors with labeling the images as real or fake to see if they could tell them apart. And it turns out they could not tell the difference and ended up classifying the images with only a 50% accuracy. Now, of course, in the 20th century, diagnostic machine learning tools play a similarly important role in the medical diagnostic process. And so to that end, we trained one tool to check if the image shows signs of the specific disease, and one tool to check if we retained patient identity. Both tools said that we met these goals with high success rates. And in keeping with real-world diagnostic processes, the patient's also going to have to make repeat visits to get these diagnostic checkups. So it would be in the favor of the attacker to control the progression of the disease in the deepfake image in order to repeatedly attack the same individual. And as you can see here from left to right, the deepfake x-rays for intermediate stages of cardiomegaly indicate a progressively enlarging heart. This kind of fine-grained control is achievable with Jekyll. The exact approach to doing so, however, depends on the attacker's resources. With more image data, they might train separate Jekyll instances for each stage. With less, they might use a single instance and instead perform image interpolation to generate intermediate stages. We also did more evaluation regarding the efficacy of this attack, and that includes evaluating multiple medical imaging modalities and multiple diseases. And I would check out our paper to learn more. So I'm going to wrap this up by trying to put your minds at ease, and I'm going to talk a little bit about defending against medical deepfakes. We took a popular supervised deepfake classifier called Viswanath and retrained it to detect these medical deepfakes. And it performed quite well, a 99% detection accuracy. Now, this would be great news, except we also found out that modifying the GAN discriminator in Jekyll allows the attacker to generate images that the same supervised classifier can only detect with a 57% accuracy. So we don't really have a robust solution, or do we? In our upcoming paper at ACSEC 20, we propose a method to detect deepfake images in an unsupervised setting. And I'd check out our paper titled Noisescope to learn more. Thank you.